let's get started for today. Welcome to the fourth installment about acids and bases. Um, to start, let's just summarize what we know so far. What is an acid? Molecule that gives up H plus, also known as a proton. All right. What is a base? Yeah, a molecule or an ion, something that takes H plus away. From another molecule. And we've spent some time talking about how some acids are better than other acids at giving up H plus. So we talked about acid strength, stronger acids are more likely to give up H plus. We talked about our measure of how strong an acid is. What do we call that number? The pKa. So a stronger acid has a lower pKa. All right, today all we're going to do is take that acid strength stuff and use those pKa values to give us a sense of how likely a reaction is. We've alluded to this before in class, but today that's what we're going to do, is just talk about what we call the equilibrium in a mixture of acids and bases. Some of you have more familiarity with equilibrium, others don't. That's okay, I'll tell you all you need to know. So in general, an equilibrium is what gets established when you have a reaction that can go in two directions. It can go forward or backward. Equilibrium is when the forward reaction and the reverse reaction are happening at the same rate, so that all the concentrations of everything stay the same. So, for instance, during the school day, let's say every hour, 100 people enter the building and 100 people leave the building. Does the number of people in the buildings change? No. But there are still people coming in, people going out. If it's just happening at the same rate, that's an equilibrium. So equilibrium means when the forward and reverse reactions happen at the same rate. So I drew this kind of generic reaction between an acid and a base. Oh, RXN. Yeah, the question is, does that mean reactions? Yes. RXN is our abbreviation for reaction. So in this case, my forward reaction would be if Y shares a lone pair with H, breaks the HX bond. I make these products, although I left something out of the products. What did I leave out of the products? The response was formal charges. Yes, there are formal charges missing. If y started out neutral, it would end up positive. If x started out neutral, it would end up negative. We also could have started with y negative and x positive, or we could have started with y negative and x neutral. We could have, the formal charges could be different in any given situation. If the reverse reaction were to happen, that would involve X sharing a lone pair with H and then breaking the HY bond. So my two directions of the reaction, forward and reverse, both can happen. And in most solutions, these proton exchange reactions are happening all the time, very rapidly. This is an equilibrium that gets established very quickly in a solution. Because it's the simplest, most straightforward kind of reaction you can have between two molecules. Because it's really just one proton that's getting passed back and forth. So the one thing you need to know about equilibrium is every equilibrium can be characterized by this thing we call the equilibrium constant, which is essentially the ratio of products to reactants. So K is what we'll call the equilibrium constant. And that's essentially equal to the concentration of products divided by the concentration of reactants. Those of you who take in AP chemistry, you might know a little more detail about this, but it doesn't really matter. For us, conceptually, we can just think of it as ratio of products over reactants. So given what we know about pKa values, I'm going to show you how you can actually find the K value for any acid-base reaction based on pKa values. To do it, we need to establish what the roles of everything in this reaction is. So in the forward reaction, what role is Y playing? Is it the thing that gives up H plus or the thing that takes H plus away? Takes H plus away. So Y here is acting as a base. HX is the thing that's giving up H plus, so that's acting as an acid in the forward reaction. In the reverse reaction, what's the role of X? Base, and HY would be the acid. So for any acid-base reaction, if you know the pKa values of the acid on the left and the acid on the right, you can find the K value for that reaction. And this is a mathematical formula. I don't want to belabor the math, but it's going to be 10 to the power pKa of the acid on the right minus the pKa of the acid on the left. All right, question? The question is the K in the equilibrium constant the same as the K in pKa? Yes, sort of. They both derive from the same place. So if you take a general chem class, you'll cover all different kinds of equilibrium constants, one of which we call the Ka, and the Ka is the equilibrium constant for an acid-base equilibrium, or specifically for the equilibrium where an acid loses its proton. So it's derived from there. In this class, it doesn't really matter that those two K, the letter K comes up in both cases for the same reason. So here's how we use this equation. If we want to look at an equilibrium and decide, okay, am I going to form lots of products or am I going to like not form many products? We can find this ratio. So here's an example. So I want you to look at this pair of reactants, and I want you to actually consider two possibilities. Looking at it, you don't necessarily have that much experience with it. I think you can imagine two possible acid-base equilibria. First, I'd like you to draw the reaction where NH3 acts as a base and CH3OH acts as an acid. Then I'd like you to consider a reaction where NH3 acts as an acid and CH3OH acts as a base. So take a minute to draw the curved arrows for each of these, draw the products you'd expect in each of those cases. All right, so when something acts as a base, what is it going to do? It's going to take a hydrogen away from the acid. How does it take a hydrogen? What part of the NH3 molecule would go out and take the hydrogen. All right, the nitrogen, what specifically on the nitrogen? The lone pair. So we're going to take the lone pair and share the lone pair. Van really wants me to say his name on the recording. So thank you, Van, for contributing the lone pair. So the lone pair is going to get shared with the hydrogen. Then we have to break the OH bond. That will give me NH4 plus and CH3O minus. If I were going to do the reverse reaction, where would I start my arrow? Lex? The lone pair on oxygen. So the lone pair on oxygen would get shared with hydrogen. Then I would break the NH bond. All right. In the second case, if CH3OH is going to act as a base, where would I start my arrows? Sammy? At the lone pair on O, and I would share with the hydrogen. That would give me NH2 minus, and then I would have CH3OH2 plus. If I were going to do the reverse reaction for that second one, where would I start my arrows? Ethan? Lone pair on nitrogen, and I would share with the hydrogen, take that away, break the OH bond. All right, so if I want to know the K value for this, I would say, what's the acid on the right-hand side? So in the first reaction, what's the acid on the right-hand side? NH4 plus. So what's the pKa of NH4 plus? You all have a pink sheet. It's, yep, Hannah says 9. And then it's going to be that minus the acid on the left. What's the acid on the left? What functional group is this? CH3OH. It's an alcohol. So that's got a pK of 16. All right. So 10 to the negative 7th. So that means, you know, that's 1 over 10 million. So that means 1 out of every 10 million molecules would do this reaction in the forward direction. So if we put this mixture together, it'll give us a small amount of CH3OH. 1 out of 10 million may seem like a really small number, but in the world of chemistry, 1 out of 10 million is not that small. If you remember the mole, so if you have a mole of molecules, how many is that? 10 to what power? 10 to the 23rd, right? So in any sample in chemistry, 1 out of 10 million molecules is still a lot of molecules. If you have 10 to the 23rd molecules, 1 out of 10 million is still plenty. All right. So this first reaction happens a little bit, is what I would say. What about the second reaction? What's the acid on the right side in the second reaction? It's a protonated alcohol. What's the pKa of the acid on the right side there? About -2. And then what's the pKa of ammonia, the acid on the left? Neutral nitrogen with a hydrogen on it. 35. All right. -2 minus 35. That gives me 10 to the -37. So 1 out of 10 to the 37 molecules would do this reaction. All right, a mole is 10 to the 23rd. So if we had a mole, how many molecules would we expect to do this? None of them. We would have to have 10 to the 37th molecules. So that would be like 10 to the 14th moles. That would be a lot of molecules before this would happen even once. So this essentially does not happen at all. So the question is there a well-known rarest reaction? Well, it if it's no, there isn't like a rarest reaction because um, you could always make up a reaction that would never happen, like in the history of the universe, because it's so unlikely. Um, yeah, so I can't give you an example of, oh, this is the rarest reaction. So you can use that pKa value or those pKa values to characterize any acid-base reaction. Let's do one more example, and then we'll call it quits. So let's take, for example, oh, who wants to pick a functional group? Sadie, pick a functional group. Pick one from the pink sheet. A terminal alkyne, all right. So I'm going to have a terminal alkyne. And let's say I were to have a terminal alkyne react with this molecule. Since one of them is negative and one of them is neutral, who's likely to act as the base? The negative one, yeah, the nitrogen. So nitrogen is likely to act as the base here, deprotonate the terminal alkyne. So on the left-hand side, the terminal alkyne would be the acid, and this thing would be the base. That means if I go in reverse, now it would be the terminal alkyne that's the base, and the amine that's the acid. For that reaction, K would equal 10 to the, all right, pK of the acid on the right, 35. pK of the acid on the left, 25. So this would be 10 to the 10th, right? So if 10 to the 10th is my ratio of products over reactants, then what that means is roughly what percentage of my molecules do this reaction? Almost all of them, right? So this essentially almost every molecule does this. So you can use that technique to decide for any acid-base reaction, how feasible is it? If you get a number that's really, really big, that means almost every molecule does it. If you get a number that is like below, say, 10 to the negative 10th, that means almost no molecules do it. And if you get a number that's, like 10 to the negative 7th, it means a few molecules do it. You'll have a few molecules in your mixture that do it. Because these equilibria are happening in pretty much every solution in organic chemistry, they become important to consider in almost every solution. So having some fundamental understanding of proton exchanges is important to understanding how every other reaction works. Any questions before we shut it down?